da nicht drunter stellen. Müssen wir. Komm nur mal in mein Alter. Oh, ich arbeite dran. Also, dann reißt aber nicht so dumme Sprüche oder so.
Okay, we'll come back to another exciting session about distributed systems. This session will be a bit packed. As you have noticed, we have extended time for the panel, which I guess was worth it. So otherwise we just could have listened to the panelists, which was great. But so we had the chance to listen to the audience as well, which was even greater. And as a result, we had two talks actually, one by Lukas Epple, who's standing there waiting to give his talk and my presentation, and we simply decided to merge. And merging two 1 hour talks into 1 hour is a hard thing to do, so we decided actually to give Lukas all the time he needs. He says he does not need a full hour. And after that, I will have to increase my speed of talk by ×2 or 3, depending on the remaining part. I remember your keynote at some conference where you were close to multimedia frame rate. Things to follow up. So, without wasting too much time, without wasting too much time on the introduction, I hand over to Lukas.
Hello everybody, I'm Lukas. So I will give a talk about distributed persistent objects today. This is my main research area since I started my PhD. So let's try to motivate this work a bit without making the database people too angry. So I don't think I have to motivate that almost all interesting programs need persistent data. But we need this data in a transactional way. So if we run, if we have persistent data and we run some functions on it or we mutate it, and at any point our program crashes, we want this data in the actual consistent state. Otherwise we have a big trouble and need to throw it away. And databases provide us this transactional data access and persistency. That's why we always, or almost always, use databases for persistent transactional data access. But let's take a step back. Do we actually need the database when we only want transactional data access? And here my work comes in, and I work on distributed persistent objects. So we want to provide persistency for data in the program without using databases. Since I already said, I work on persistent objects, so let's see if we don't use a database, what can we get as a benefit? So we can maybe integrate the persistency directly into the program. That is nice. Maybe we could use the same object representation for the persistency part and for the actually runtime in the program, at the runtime in the program, so we don't have to translate between the consistency layer and the actual application. And maybe we can avoid the query processing, interpretation and parsing of queries. And if we are using objects, the benefit is that developers already know how to handle objects in the program. If the persistency comes on top, they don't have to do anything or learn anything new. So let's start with persistent objects on one local machine. For persistent objects, we want 4 things, which is persistency, which is clear, I think. Persistent object without persistency doesn't make any sense. Then we want to use objects of almost any kind. So if the user or the developer designs a class, we want to use this class, we want objects of this class to be easily persistent in our system. And of course, we want transactional behavior to not end up in any inconvenient or inconsistent state and end up with corrupted data. And of course, we want speed, we want performance of the system be as fast as possible. Okay, for the first start for persistency, we need some kind of hardware. So in a perfect world, we would, if you could wish for a hardware, the hardware would probably be infinitely cheap, infinitely fast, persistent, and infinitely durable. But currently we are stuck with the memory hierarchy. You can see on the right, we have at the top non-volatile, very fast storage hardware, and at the bottom, slower, persistent, cheaper hardware. That was true until March 2017, when Intel released their Intel Optane memory. And it was released as a SSD and DIMM form factor. So here you can see such a DIMM stick. You can stick it directly into a RAM module, into the RAM on your motherboard, and it works as a non-volatile RAM. For the performance, it is closer to actual RAM. As you can see, the latency is 170 nanoseconds on sequential reads and writes, and 300 nanoseconds for random reads and writes. So there seems to be some buffering internally, but we don't really know because Intel doesn't tell us. And DRAM gives us 80 nanoseconds latency, whereas modern NVMe SSDs gives us 60 microseconds. So we are much faster for latency. Also here for the bandwidth, SSDs only give us about 200 megabytes per second, whereas DRAM on our system gave us 5.6 gigabytes per second, and the Intel Optane gave us 1.4 gigabytes per second. This is random write performance. For the durability, DRAM of course is infinitely durable. You cannot, or you can hardly damage it by writing to it. Durability of Intel Optane is also much higher than from SSDs. This is 360 petabytes written before it dies, or it probably dies. Intel says it at least 360 petabytes written, otherwise it's in guaranteed form. So now we are here. This is the new memory hierarchy. We have NVRAM, Intel Optane NVRAM, which is non-volatile and has a much better performance than usual SSDs, but is still persistent. For the price, it was cheaper when it was released. Right now it's a bit more expensive than actual RAM, but I will come to that later why that's the case. So I will now give a short introduction how this memory actually works, or how it works, how we think it works, because Intel actually does not tell us what they are doing, and all of this part now in the presentation is inferred from old research from Intel they told us about, from patents they filled in, and so on. So Intel has memory cells, you can see here, and they are filled with some kind of material which can be in one of two states. It can be in an orderly state, represented here, and in the chaotic state. The orderly state is some kind of crystalline structure, while the chaotic state is just something else. So, and in order to write and read from this, we need a way to transform, to come from the orderly state to the chaotic state, and back from the chaotic state to the orderly state of the material, so we can switch a 0 to 1 and a 1 to a 0. How this works is, when we come from the chaotic state, we apply for a long amount of time, or long is relative here, for a long amount of time, a small amount of voltage, and this restructures the elements in the memory cell to go back to the orderly state. The other way around works like this. For a very short amount of time, we apply a high amount of voltage to memory cells, and this kind of shocks the material in the memory cell, and the orderly state is deformed to a chaotic state. In order to read from such a memory cell, we apply a small amount of voltage for a small amount of time to not disturb the states of the memory cell, and then the voltage given, and we measure the resistance of the actual material, and both of those states of the material have different resistance, and that's how we can infer in which state the memory cell is, and therefore we can assign a 0 or 1 to it. We actually don't know if the chaotic state is a 0 or 1, but you get the idea. So okay, we now have, so it seems that we have some kind of this magic memory we wish for. It's performance-wise close to RAM, it's durable, it's bandwidth, the bandwidth is also almost as high as DRAM, or at least comparable. But it's really that's not that simple. So there are some problems. We still want to write transactionally to data in VRAM, but Intel Optane already guarantees us atomic writes for 8 bytes, so that's not really what we want. And working with the persistent storage is not really trivial. I will give some examples about that now. So suppose we have a struct A with 3 members, A, B, and C, all of the type int. We can allocate, NV allocate is now a made-up function to allocate memory on the NVRAM instead of the DRAM. It doesn't really exist, but it's not that much more complicated to allocate on an NVRAM. But then we have the struct A allocated in the NVRAM, it lies flat in there, there's no problem. If you now have a struct B, on the other hand, which has a vector of int as a member, we allocate memory on the NVRAM for such a struct B. Now we have a member F, which is a vector, and this vector allocates data by itself and allocates on DRAM. So now we have a pointer to a struct B, and this struct has a pointer which points into DRAM. If now our broker crashes at any point, and we can reconstruct struct B from the NVRAM, but the pointer in F points to DRAM, and we now are in an inconsistent data state. So this breaks the whole transactional model here, because if we break at any point and the DRAM is nullified, the pointer points to a memory region which just contains trash. Another problem is if we want to do such a thing with a struct A, we want to assign 5 to one member and 6 to another, and if our broker crashes between lines 8 and 9, we are also in an inconsistent state. We did not execute those 2 lines transactionally, but only line 8 was executed, and that's also in inconsistent state. So it seems that we need some software support for this. And actually Intel provides some libraries for this. There's libpmem, which is very low level. There's libpmem object, which is a C library. It provides transactional behavior and data access with undo logs. And then there is libpmem object, CPP, which is a C++ wrapper. It also provides transactional behavior with undo logs. But on top, it also provides a lot of data structures like vectors, strings, smart pointers, heaps, queues, everything you can think of. And those data structures have the property that that all the methods of the data structures are actually implemented in a transactional way. That's really nice, but it violates some of the requirements we made earlier. We want an easy translation between persistent and volatile objects, but that's not the case anymore. If we are forced to use all the data structures from the Intel library, then we have to translate between runtime and persistent objects again, and we do not want that. And also there's another problem, which is a pretty big one, and that's that Intel Optane was discontinued in 2022. So Intel does not produce or research this kind of memory technology anymore. So it's maybe not the best idea to continue using the library. We want maybe something technology independent to be future-proof if there is a new NVRAM technology which maybe does not provide this 8-byte atomic write functionality. So let's see what we can do. What do we actually want? We want persistent storage, of course. And now we are using memory map files, because you think, okay, when using memory map files, in the end you just get a pointer and a length. And you can do this everywhere. You can even if it's not a good idea, to use memory map files for this kind of technology on a non-NVRAM, but on a normal SSD. It still works, it's much slower, but yeah, you can still test the whole setup and the whole system on a system which does not actually provide NVRAM. And when switching from an NVRAM system to a non-NVRAM system with this, you just have to change the msync call. So it's just one line of code you need to change to actually to actually run this whole system on a non-NVRAM system. That is of course much slower. Okay, then we want the easy translation between volatile and persistent data structures. And because we have this easy translation between volatile and persistent data structures, we can actually just have an object cache which holds all of the objects or some of the objects in RAM to provide really fast read access to this stuff. And of course, we need the transaction rights at the end. So this is the rough architecture. In RAM, we have the object cache. They point to the same object in the persistence manager where it's stored in the NVRAM, and we can go from the persistence manager to the object cache representation, and from the RAM to the persistent representation of the object. So how can you get a transaction-like execution? So given this initial memory layout, we have a header so this is the NVRAM. We have an OK bit and a version. Actually, there's much more, but for the sake of the argument here, we only need the OK bit and the version, and then the object representation flattened out here in the NVRAM. And now, if we're given a function f, we want to execute transactionally, we execute this f on the object in the cache, and then we copy it back to the NVRAM as a second version, but we do not set the OK bit. If we want to commit at this point, we set the OK bit, and now we know, okay, the OK bit is set, the version is higher, so this is the new object. So now we have this new version of the object in the cache and in the persistence layer, and we can just continue with work. If you want to do a rollback, at this point, we just do nothing in the NVRAM. We free the memory here, and then we copy back this version of the object to the cache, and then it's done. So in the end, we can free the memory. Here, we don't need anyone to provide history or something like that, just throw it away. So that's how we can provide transactional behavior in the VRAM. So, but that's only on a local computer. So, yes?
Question to that. So, that just works in the transaction, just covers one object, right?
Yes.
Transaction covers more than one object.
Yes, exactly. So, but I will tell you later how it works with more objects. Okay. Yes?
We had this example with the linked file.
Yes.
How does that apply to this? It doesn't work, right?
So we have this very small translation process where we flatten out.
You have to serialize.
Yeah, you have to serialize. But you can actually use the internal, since you're not writing to like the vectors, you do not push back into the actual object. It's just read only in the persistent and VRAM. So you can flatten out the pointers. Like if there's a pointer, you can just append it to the object itself. Yes.
On slide 15, it looked like the RAM has the same same size as VRAM.
Exactly, yeah. This is for this showcase only. You can of course apply all kinds of caching technique you want here.
Thank you.
Okay, oh, sorry. So until now we only covered how we can perform. Okay, so how we can provide a single transaction on a single object on a single machine. So, but you want to provide this for more than one machine in a distributed setting with more machines which all have NVRAM, and the objects are distributed across them. So let's go into the distributed persistent objects part of this presentation. So this is the setup I will use for this part of the presentation. We have 2 nodes, N1 and N2. Of course there could be more, but for the sake of the argument, we only use 2 here. And they have objects A to D and B to H. Yes. So, but now we have some new challenges. We need a way to reference non-local objects. We need a way to reference objects on another machine. That's actually pretty easy. We just give each object a unique ID, and then we can look it up in this distributed setting. We can do it with a centralized lookup or a distributed hash table, and then you cache it as long as the node N2 does. For example, if N1 has a reference to E, and N2 doesn't tell N1, okay, I don't have this object anymore, N1 knows this reference is valid and can just use the reference without looking it up again. Then the second part, we need a way to select subsets of all objects based on properties. For example, something like, give me all users with the name Christian, and then I want this subset of all the users of all objects with the field Christian. We want to query for single objects. That's pretty easy. That's just querying for subsets of the set 1. So that's the same problem, almost. And then we want a way to execute transactions on all of those objects. So in such a way that they commit on all objects, or they roll back on all objects, and in a sequential consistent way. So for the subset selection, we choose the basic concept of lazy iterators and higher order functions. So for example, Scala provides this. You will filter, map, and fold left. With the filtered map, you can filter out elements you do not want in your view. With map, you can transform the elements of the view you had before into new objects to actually perform more filters on them or something like that. But I will have an example later how it works. The fold left operation is an operation which iterates through the collection and then calculates on each element some kind of final result, and this example would be the maximum. And it starts with 0, and then it performs the maximum function on 0, the first element, the result of that on then the maximum of the result of the first maximum call with the second element, and so on. And in the end, you have a single result. So this is so prominent that even C++20 introduces this kind of concept. C++20 introduced the fuse with filter and transform. Transform is another name for map. And with C++23 we have forward left, which does exactly that. And the observation here is that nothing really prevents us from using this in a distributed setup. MapReduce does this, and it's a distributed setup. So we use this pattern to actually use it in our system to select subsets and then perform transactions and information extraction with the reduce function from the objects. So what we provide is the three functions, map, filter, and lm. What they do, I will explain it later perform actions, which is the reduce, which is read-only, but you can collect information from the system, or transact, which actually writes to the single objects, and you can modify them with this function. So suppose you have n1 and n2, and they have integer values, ln 5, 20, and 100. And we now want to search, or we want a subset of all numbers where the string representation has exactly 2 characters. We perform the few, we start with a few of integers, which is the whole, which are all objects. Then we perform a map with .string function. We get the string representation of the original objects. Then we filter out all elements where the string representation is not of the length 2. And in the end, the .element function gives us back the original references, original elements, gives us back the original elements of the maps. So in this case, this would be 11 and 20. So now let's see how the 2 actions actually work, the transact and the reduce. So the observation is here that if you want to use fold left, we would need the result of another node before a new node could start its fold left, and we do not want that. We want to execute this fold left on all machines at the same time, to not wait on the results to not wait for intermediate results from other nodes. So we cannot use this bare fold left. And the idea is all nodes execute their fold left method, create an intermediate result, and in the end we give it to a combinator function which combines all of the results to give us one end result. So we slightly modified the type signature. We still have the initial element, the operation, which performs the fold left, and then we also need to pass a combination function which combines different end results to one single end result. And this does not only allow parallelization across the nodes, but on the node itself. For example, one node can split its elements in 4 parts. They all perform fold left, and in the end they combine the results to one end result. Yes?
When you go one slide back, does it actually change the object where you have the 2 nodes with the 4 objects, one back? Yeah. Does it now change? Is object 5 still there?
Yes. It's still there.
So it's a view.
Yeah, exactly. It's a view.
At some point.
Yeah, you are not allowed to mutate the object or to move it anywhere to view. It's a view, and it's also lazy evaluated.
Okay, so when you remove somehow the view, 5 and 100 are there.
Yes.
But within the view, they are not anymore.
Exactly. Yes.
Yeah.
It's just a subset selection of all objects. So this would be that's how such a view would look like. For example, we have a view of integers. We need to call create. Then we map those integers to strings. We filter out all strings which do not have a length of 2. Then we call .l to get the original integers back, and then we call the reduce function starting with initial accumulate of 0 for the left function is the max, and the combination function for the maximum is also the maximum. And in the end, you need to call it .build, but that's just our builder pattern. Okay, so now we have a way to select subsets of objects and to extract results or to extract insights of those objects in a read-only way. But you need a way to mutate those objects in a transactional way, and we only know that for one element right now, but you want it for more than one element in a sequential consistent way. And right now, if you look at this example, for example, you have a transaction, a mutated transaction, T1 and T2, and those transactions want to get executed. T1 is sent to is want to be executed on the object D and the object E. And now, if you both nodes have the problem that they do not know which transaction to execute at first, so we have this kind of problem. For example, if N1 was the initiator of transaction 1 and N2 was the initiator of transaction 2, naturally N1 would see transaction 1 at first, N2 would see transaction 2 at first, and then we end up in an ordering of the transactions or in the execution order of the transactions on the single objects in an inconsistent way, and we do not want that. So the solution to that is actually, So the solution to that is that we build a tree, given all the nodes, we build a tree which is statically redefined at compile time, and then every transaction is sent to the lowest common parent of all objects involved in this transaction, and this node, this parent node, then orders those transactions in any way it wants, FIFO ordering or whatever. So it would look like this. Transaction T1 and T2 want to be performed on object E and object D. So in this tree, they send it to the lowest common parent of N1 and N2, which is N3, and N3 then decides the order in which the transactions are executed and awaits the results. So that's how the basic system of us works. As a conclusion, I think the NVRAM is a pretty promising technology, even if it's discontinued by Intel. We hope that some other vendor will pick this kind of technology up. There are some other NVRAM technologies out there which are currently only in research state, not being produced. And we have seen that we can execute distributed transactions with our databases. And I think the views are a pretty powerful abstraction for the interaction with subsets and the selection of subsets and the extraction of information of those distributed objects. So that's my talk. Thank you for listening. Those are my colleagues or the students which worked with me on this project. If you have any questions, you can write me or ask me now. Yes.
One more. So that one with the two transactions. So why shouldn't node 3 say instead of having T1, T2 executed 2 times, say T1 goes there, T2 goes there, and it may be that T1 looks into the object in N1 and T2 only in the object of N2.
Yeah, that's true. So you have to send the transactions to the lowest common parent in the tree of all objects involved. So in this case, but if you do not know which objects are involved, then you have to send it to the root of the tree. So
yeah, but this looks like transaction 1 is executed 2 times.
No.
No?
No. Why?
Well, what is node 2? Node 2 doing and what is node 1 doing?
So node 1 executes transaction T1 on the object D, and node 2 executes transaction T1 on on object E. So it gets executed 1 time on each object involved.
Okay.
But the more local references, or the more references you have to the remote objects directly, the lower you can send the transaction in the tree and save communication overhead. But if you do not know for a few, you have to send the transaction to the root.
Thank you.
I guess this is now my try to take over and fit 60 minutes or 50 minutes into 25, which would work.